Welcome to mode concept. This is the practical aspect of introduction to embedded systems, which we have done the lab 1. So now this is the lab 2. In this our lab 2, we shall be interfacing an LED with an MCU, that is microcontroller unit. Our main objective is to understand and equally get conversant with the different modes of interfacing an LED with a microcontroller unit. Our requirement still remains as it were Pro Tools simulation software, micro basic compiler, power supply source, breadboard, PIC microcontroller, that is PIC 16F628A, and so on. Now, there are different modes of interfacing LED. But first of all, the LED itself has a way it is designed. It has two pins. The long pin stands for the anode, while the short pin stands for the cathode. So the intensity of the LED depends on the current it is receiving. When you give the LED more current than it requires, it burns it off. So there is a particular required current that is meant to work with the LED. So, and each port of the microcontroller unit has a maximum current it can deliver. When you draw more current from that particular port than it can deliver, you damage the port. So when doing our design, we have to make sure that we don't draw more current from a particular port more than it can deliver. So to achieve that, we bring in a current limiting resistor so that to limit the current that will be drawn from that particular port, and to make sure that the LED does not receive more current than it requires. So different colors of LED requires different voltage drops and has different forward currents, as you can see on this table, the red, the range, and so on. So to do our design proper, we usually use this Ohm's law formula, where V equal to IR, R equal to V over R. So our V here is the source voltage minus the diode voltage over the forward current of the diode. So the port delivers 5 volts. Then the diode requires 2 volts. If you now do 5 volts minus this, you have 300 volts. So for a particular type of LED that requires a forward current of 10 milliampere, you do this calculation, it will give you 300 ohms. So that means you need 300 ohms resistor to drop the voltage so that it doesn't burn out the LED and keep the LED the required current, so I don't overdraw the current from what the port can deliver. So there are two modes of interfacing a LED. We have the current sourcing mode and we have the current sinking mode. In the current sourcing mode, you provide a high signal to turn on the LED. And in the current sinking mode, you provide a low signal to turn on the LED. That's when you provide a low signal, the LED comes up. Then on this current sourcing, we provide a high signal, the LED turns up. So now let's go to our diagrams. So this is the diagram of current sourcing when we interface in current sourcing mode. The LED sources current from the microcontroller. You can see comes to ground. So whenever you provide a one here, the LED comes up. In the current sinking mode, the LED sinks current into the microcontroller. Whenever you provide 0, because 1 is available here, when you provide 0, the LED comes up. So let's go to our procedure, which we will just start doing, not just reading. So in this our procedure, I'm going to open my Pro Tools. I have it on my taskbar here. So my Bluetooth has opened. I'll just go to schematic capture. So I'm on schematic capture now. I'll just go to P to pick my component. So I need PIC 16F628A. So I will double click on it to pick it. I need a resistor min res 1, okay, retard R, that is it. I'll pick it. I need a LED LED red, that is it. I'll pick it. What again do I need for my Bluetooth simulation? I don't need any other thing. I'll just go to OK. Now I will drop my PIC. I'm going to zoom so that I will see my work better. Move shift my map. Okay, then pick my resistor. Remember, we always do our design first before we write the code that will drive whatever we have designed. So in my circuit diagram, I have my LED attached to port B.0. That's important, port B.0. So I'm going to attach my LED at port B.0. So I'm going to pick my LED and drop it. I'm going to get a ground and drop my ground. Now I am done with my connection. This is my connection. I am done with it. I now have to go and write a code that will drive this man. So what I will do now, that I have written my code. This is my code. I'm going to copy this my code to my compiler and compile it. You can see my code. Program to blink. LED 3b.0 equal to 0. That means the bit of 3b, the 0 bit of 3b alone. We don't want other ports to come up. We want just that bit of port B.0. That is why we will say 3b.0. We would have said 3b equal to 0, meaning all the port B's, but no, just want the 0 bit of port B to be equal to 0. That is be an output port, because it's the 3. Then port B.0 equal to 0. So we're just enabling the port B.0 bit of port B, only that particular bit. Other ones remains off to disable all the comparators. And now raise high that same port B.0 to put it to make it 1, because we are using current sourcing mode. Wait for this length of time, 0.5 seconds, and now turn it off at same port 0 bit. So and now wait again when it's off, wait again for this length of time and go back to start. That is, it will keep on blinking until we'll stop the simulation. So I'm going to copy my program. I've copied it. I'll go to MicroBasic. Actually, I am supposed to write this program inside MicroBasic and compile it, which is how it's supposed to be. But since I have already written it before, just to prepare for the class, that's why I just have to avoid that delay of retyping. I now have to copy it and paste inside my compiler. So my compiler is open. I'll just go to new project, standard project. So choose my project name. I'll call it LAB2 to CTE205. Now, if they want to save it, I have to choose a particular folder, as I said, as we've been doing. So, choose this folder. Okay. My PS is already here. I'll just change my oscillator to 10 mega, because that's what I want to use during my design. So, I'll finish. So, I'm going to highlight from declaration and leave my program title because it's important. So from this, I say Ctrl V, good. So I'll just remove this. It's not important for us. Now, this is our program. Everything is in good shape as we desired it. So, having explained this program, I'll go straight and save and build program. Save. I'm going to build the program. Okay. So, having debugged my program now, it has run. Took me late. Project length successful. Finish successful. So I will just go to my design, Protus, and run my simulation. But before I run my simulation, I have to fetch my code and upload it into this microcontroller. I'll double click on this microcontroller as usual. Go to program file. Documents. CTE20522, that's where we saved it. So call it CTE. We call it LAB2 CTE205. Look at it there. That is it. I'll double click on it. So change my clock frequency to 10 megahertz as chosen our program. Okay. Just click. Then let's run simulation and see what happens. You see, our LED is blinking. That is to tell that we are done. If we transfer what we have done to a real hardware, this is how it will still be blinking. See, all other ports are off because we only choose port B.0. Other ones are off to save our power. So, thank you for watching this design. But before we finish it up, let's look at other part of our lab. So that's the program for current sinking mode. When you make your port B.0 equal to 0, that means you are turning on. When you make it equal to 1, you are turning off. That is the opposite of current sourcing. So, but all through our labs, we'll be using current sourcing mode. We'll not use current sinking. So now see, this is our simulation results as we saw in the Protus simulation we just carried out. So now make your observations and write them out. Equally write out the precautions you took. At least myself, I observed that the LED blinks after simulation was started. Now the precaution, I ensured that my code was written after I have done my design to make sure that I did not make any mistake in my pin selection or in port selection. I equally wrote my code and build it, save it and build before I now go to run simulation. And in my coding, I equally ensured that I debugged my code very well when it did not run to make sure that my code runs successfully. So in conclusion, your code must run. Since my code must run for me to carry out a successful simulation. If my code did not run, I would not be able to generate hex file that my simulation design, my design requires proper. So that is that. Thank you very much for watching this lab. do well to like the video and drop a comment. Subscribe as well to catch other videos I'll be dropping very soon. Bye.